Hi everybody, Dr. Rutner here. This is the video for the paired t-test. This is the last of the mean hypothesis tests that we're going to be working on. And the good news is that if the situation that you are trying to do a hypothesis test for leads you to this particular test, this is actually one of the simpler and more straightforward procedures that we've got to look at. So we should be able to go through this fairly quickly. We're going to take a look at the conditions that would lead you into a paired t-test, and then of course work through the computations using an example. So the situation that we're looking at here we are evaluating a numerical variable. We're interested in comparing means of numeric variable, but the thing that really makes this one distinctive is that we've got some kind of a logical, identifiable, defensible way to match up the observations in the two samples that we're looking at. And so examples of this might be doing a pre-test and a post-test. That's kind of the classic example. So for instance, if we're doing some training and we want to know how people are actually responding to the training, whether they're improving their performance, that kind of thing, what we could do is we could do a pre-test on them before the training, put them through the training event, and then do a post-test afterwards and match up for every individual who goes through the whole thing, match up their before score and their after score and actually look at the difference, look at the change. And so in that case, we're matching up two different scores from the same person, and that's our identifiable, defensible way to do that matching. Another example, and this is actually similar to the problem that we're going to look at, might be that we're have individuals rating multiple products. And so in order to help us control for possible variability in the way people view things or the way people perceive different types of products, what we might do is match the ratings of individuals by the different product that it is that they're evaluating. So that's another option. And I've got a couple of other examples in the slides later on. But the key characteristic of a paired difference t-test is that we do have to have some way in order to match up those individuals or match up those items in the sample. They don't have to be people. We also are assuming that our differences are normally distributed. And in fact, what we'll really be testing is testing a sample of those differences. Or if we can't make that normal distribution assumption, then we have sample sizes that are 30 or greater, so we can rely on the central limit theorem. You can see there's a little formula here. What we are actually evaluating is going to be for each pair of observations that we have in the two samples, we're going to be evaluating the difference between the observations for those pairs of samples. And so that group of differences represents the sample that we'll be evaluating in order to make an estimate about the population of differences. All right, so here's a couple of examples, and I want to walk through. One of these is going to be a paired t-test, like we're talking about here. The other is going to be an independent type of test, like we were talking about in some of the other videos. So here we're interested in comparing viewing habits, TV viewing habits between men and women. And so in one situation, we're randomly selecting 20 men and 20 women and just comparing how much time they spend watching TV. The other situation is that we randomly select 20 couples and we compare the time that the husbands and the wives spend watching TV. Now, if we were doing this in class, I would ask y'all to tell me which one you thought is the paired t-test and which one you thought is the independent samples t-test. Take a second, think about it. Hopefully it makes sense to you that our first example here is independent samples. We don't have any logical way to match up a particular man with a particular woman in the sample. And so really what we're going to get at there is, independently speaking, do men and women have different amounts of time that they spend watching TV? Whereas in the second example, the husbands and the wives are already matched up, right? They are couples. They're couples who live in the same household, presumably, and have at least similar TV viewing habits or similar interests, or at least we would think possibly some overlap in terms of viewing habits and interests. Perhaps, similar obligations outside the home, whether it's kids playing sports or other interests that they have, or similar views on TV watching. In any case, we would expect to see some potential similarity between the husbands and the wives in these couples. And so what we can do is by matching up the married couples, matching the husband and the wife, and still comparing TV viewing habits, that allows us to control for variability in those kinds of factors that I'm talking about, right? So, maybe couples who have young kids at home that are involved in a lot of sports aren't home very much to be able to watch TV. And so perhaps that affects the husbands and the wives both. And so we're able to control for that kind of variability. Whereas in our independent samples in the example above, maybe you get some people who have outside obligations, maybe you don't. We don't know if those kinds of individuals are equally represented in the two samples. And so the paired t-test, by matching up the husbands and wives, allows us to control for that kind of variability. All right, one more example to look at. This one is not looking at people. This one is looking at samples from stream water. And we're interested in this case, zinc concentration in the streams. And so let's look at our two examples. Samples of water were taken from 10 different streams located close to manufacturing plants. For each stream, one sample was taken upstream from the plant and one downstream. Mean zinc levels are compared between the upstream and downstream sample, right? So zinc level is a numeric variable. We are comparing the means of different water samples in this case. And so the question we're asking is, are those independent samples or are those paired samples? Now, before we try to answer that question, let's look at the other example. In this case, we're talking about samples of water from 10 streams located close to manufacturing plants and 10 streams which are not close to manufacturing plants. And again, what we're doing is we're comparing mean zinc levels between the two sets of samples. So one of these examples represents independent mean comparisons. The other one represents paired mean comparisons. Which is which? All right, so let's think about that. In the first example, the first bullet point, do we have a way that we can logically match up one sample or one water sample in one group with one water sample in another group? And I think, yeah, we do, because we have a pair of samples taken from each stream. The way they differ is whether they're upstream or downstream of the manufacturing plant. So we can match the samples up by stream, the samples in the two groups, we can match them up by stream. Whereas down here, yes, I've got 10 samples from streams close to plants and 10 samples from streams not close to plants. But with the information that I've got provided, I don't have any way to logically pair a particular stream from the close sample or the close group to a particular stream from the not close group. There may be something out there that we don't know about, but with the information I'm provided, I really don't have any way to match those up. So this is the kind of analysis that you need to do as you're evaluating one of these problems. Do you have some information to make a conclusion that there's a logical way to match up items in one sample with items in another sample? Just as kind of a clue to sort of help you figure that out, do notice that we're talking about samples that have equal size here. If you're going to do a paired t-test, right, that's what we're talking about here is a paired t-test, then your sample sizes must be equal to one another, right, because you're matching them up. You have to match them up. If you're doing independent samples t-test, like the second example that we have here, where we don't have a logical relationship between them, then you may have samples that are the same size, or they might be different. So in this case, I gave you 10 and 10 just to avoid giving it away too easily. But it could have been 10 streams close to plants and 12 streams not close to plants, or some other set of possible numbers. But if you're doing a paired t-test, then you really need to have the same number of observations, or two observations for each of the items that you're looking at. All right, so hopefully that makes sense. If you still have questions about that, of course, please let me know and we can talk about them. All right, so with that in mind, let's take a look at some of the computations that we'll be doing. The computations are going to be that we are really looking at the difference between observations in the two sample, and that's what this first formula is representing. So D sub I represents the ith difference out of our set of differences, where we compute each of those differences by taking the ith observation in group 1 and subtracting the ith observation in group 2. And so, for example, in our streams, if we're looking at zinc levels, we'll subtract upstream zinc levels for one stream from downstream zinc levels for the same stream and get the difference between the two. Do that for all of the streams, and then this group of D sub i's is really the sample. Excuse me, I exported too quickly. That's really the sample that we're looking at, is this sample of differences. All right, the point estimate for the mean difference is what we call D bar, so the average or the mean sample distance, and we can compute that by taking the sum of all of our individual differences and dividing by the number of differences. So that's just a simple mathematical arithmetic average there. And then we can also compute the standard deviation of those differences. And again, this should look like a pretty familiar formula. I'm just using D's instead of X's here now. And so we compute that standard deviation by taking the squared sum of the differences between each individual difference and the mean difference. I realize I'm using the word difference a lot in that explanation, but I don't think there's any way to get around that. So we compute differences for each item, compute the arithmetic mean of those differences, and then use our normal kind of standard deviation computation to compute the standard deviation of those differences. Take the sum of the squared differences, divide by sample size minus 1, take the square root of that, and that gives us our standard deviation. All right, so those are some basic computations about differences. Let's take a look at the kinds of hypotheses that we're going to evaluate here. And you'll notice that these hypotheses are stated a little bit more simply than the other two sample hypotheses we're looking at. Because as I say, what we're really doing is we're not hypothesizing about two populations now. We're hypothesizing about a population of differences between two populations. So again, a little confusing to talk about, but really it's the population of differences is what we're hypothesizing about. So here's an example of a lower tail test set of hypotheses, and as I hope you expect by now, we've got our region of rejection, our alpha value in the lower tail of the distribution that we're dealing with. If we have an upper tail test, so we're hypothesizing for the alternative that the mean difference is greater than 0. We put our region of rejection in the upper tail of that distribution. And of course, we can do a two-tailed test where we hypothesize that the mean difference is equal to 0, with the alternative being that it's not equal. And in that case, we split the alpha, split the region of rejection between the two tails of the distribution. And then, of course, you can see rejection rules for each of those. You can tell just from the way we've got these distributions set up that we're working with a t-distribution here. And so hopefully that will keep things fairly simple. The good news is that the computations are going to be a little bit simpler than the previous two examples. All right, so Our t-statistic is going to have n minus 1 degrees of freedom, where n is the number of pairs that we are considering. All right. So to compute our t-statistic, this is the test statistic that will compare to our critical value of t. We're going to take d bar, which is the mean of the differences, subtract our hypothesized mean of the differences, and then divide by the standard error of the differences that we get by taking the standard deviation divided by the square root of the sample size. And again, working with a distribution that has a t-distribution with n minus 1 degrees of freedom. All right. Confidence interval for the mean of the differences, we're going to take our point estimate, which is d bar, that's the mean of the sample differences, and then add and subtract a margin of error, computed as the t-value for 1/2 of our alpha value times the standard error of the differences. All right, so same basic computation we've been doing, just working with slightly different notation to reflect the slight variation that we've got in terms of our concept here. All right, so let's take a look at an example. 9 experts rated 2 brands of coffee. We have Cartagena Morning and Bogota Velvet coffee in a taste testing experiment. They rated the coffees, the 2 different coffees, on 7-point scales from extremely unpleasing to extremely pleasing on 4 different characteristics: taste, aroma, richness, and acidity. And then we computed an overall sum of those 4 characteristics, an overall accumulated score. And what we are interested in testing is, at the 0.05 level of significance, is there evidence of difference in the mean ratings between the 2 brands? All right. So a couple things to talk about here. First, this is not necessarily related to hypothesis testing, but first, you'll probably recognize this type of scale, a 7-point scale, where what we really have here are ordinal values that we're assigning numbers to. You'll probably recognize that as something that we talked about with data types in the beginning of the semester and scale types. So a scale of extremely unpleasing to extremely pleasing is really, by definition, it's an ordinal scale, not a numeric type of scale. We're assigning numeric values to it, and in this problem, we're going to treat it as numeric data. But if we're going to do that, we have to rely on some assumptions that the people who are using this scale are interpreting it in a similar fashion. So that, for example, the difference between extremely unpleasing and whatever the next item is, maybe somewhat unpleasing. So the difference between 1 and 2 is going to be interpreted consistently across the experts who are making this rating. So there's a couple of ways that we could claim that. We could claim that we've tested the scale across several different people. We could also claim or look for evidence that the people who are using the scale have been trained in how it's used. And so with some of that evidence, we can take this ordinal data and treat it as though it's numeric. We're not presented that evidence in this problem statement, but I did want to point that out since it's something that we've talked about several times previously. So we're going to assume that the evidence is there, and we can treat this as numeric data. That being said, do we also have something in this problem statement that lets us believe that we're doing a paired t-test? So we're able to pair up ratings, and I think we do. We have 9 pairs of ratings, 9 experts who rated 2 coffees apiece, and what we're interested in doing is comparing for each of those experts differences between their 2 coffee ratings. What this allows us to do, as we said, paired t-test really allows us to control for some variability. So, perhaps people have different palates. Their palates some are more sensitive to acidity or less sensitive to acidity than others. People may have preferences, those kinds of things. It allows us to help control for those kinds of individual variations. So we're doing a paired t-test. We have a small sample size. Our sample size is actually going to be the 9 experts in this case. Small sample size, so we do have to assume that these ratings are coming from normally distributed populations. But if we can make that assumption, then we can do a paired t-test. All right, I am going to go ahead and flip over to my write-up for this t-test and also take a look at the data that we have for it. And let's take a look here. And actually, let me just delete these formulas because I'm going to recreate them with you here just for a moment. So I'll delete those formulas and we'll rebuild those as we go. But here is the data that we're working with. So we have our 9 experts. They're identified by their initials here. The initials aren't really important. It's just to reinforce the fact that these really are people. And for whoever CC is, that person rated Cartagena Morning with a grand total of 24 on our summated scale, and Bogota Velvet with 26. SE gave a 27 to both. EG gave a 19 to the Cartagena Morning and a 22 to the Bogota Velvet. So you can see those are the actual scores from the experts. And then what I've done over here is just written a little formula. I'm not going to rewrite this one. This is a fairly simple formula. Just written a little formula to compute the difference between the ratings of the two coffees and then copied that down. So we're computing that difference for all of them. You can see actually I've got I've got a positive number, I've got 1 0, and I've got a whole bunch of negative numbers here. So apparently people seem to like the Bogota Velvet maybe a little bit better than the Cartagena Morning, just kind of eyeballing our results. We'll have to do the test to see if that's actually a significantly different or the statistically significant difference in the ratings. All right, I've got some information down here. We are hypothesizing a mean difference of 0. Let me go ahead and show you our hypotheses. We're hypothesizing a mean difference of 0. We're setting this up as a two-tailed test because in the problem statement, we're asked to determine whether there is evidence of a difference in mean ratings. Had we been asked to determine whether the difference was positive or negative, then we would have a one-tailed test. But in this case, we're just asked to determine whether there is a difference in the mean ratings. So that's a two-tailed test, where our alternative is that the difference is not equal to 0. All right. We are testing the 0.05 level of significance with a sample size of 9. And then going through, and actually I think I've got the same verbiage repeated twice here, so I'll clean that up before I post this. But going through and looking at our explanation here, let me blow this up for us a little bit so y'all can see it better on the screen. Going through and looking at our explanation, I've just written out some of the things that that we talked about as we were talking about what technique to use. So we're talking about the assumptions, we're talking about treating the ordinal scale as numeric values and those kinds of things. So we've got that. And then coming down here, coming down a little further, we have our decision rules or rejection rules as I sometimes call them. We have an alpha of 0.05. We have 8 degrees of freedom, n minus 1, 9 minus 1 degrees of freedom. We can look the critical value of t up in the scale for an alpha of 0.05 and 8 degrees of freedom, and that comes, look that up in a table. Comes out to be 2.3060, or we can use our t-inverse two-tailed function to find that value. So we can state our rejection rule that we're going to reject the null hypothesis if our t statistic is less than the negative critical value or greater than the positive critical value. And I'm actually giving you several variations on the rejection rule here. We can state it in terms of p-values or in terms of our confidence interval as well. Let me go back to the spreadsheet for a moment and kind of catch up with the computations that we're doing here. We've already computed our mean differences for each of our experts. I'm going to go ahead and count how many differences we have. So that will be my sample size. I'll compute the average of those differences. And I'm just going to do that using my average function. So that is d bar, or the mean of the sample differences. Degrees of freedom is sample size minus 1 And then the standard deviation of the differences, I can compute that with my standard deviation formula for a sample. So stdev.s is the function that I'm using here. And I just want the standard deviation of that group of differences. All right, so that's kind of my starting data here. Let me also come down and I'm going to go ahead and do the critical value. Since we've already stated it in our rejection rule, we'll just verify that it's right. And we'll use the T inverse two-tailed function because we're working with a two-tailed hypothesis. Put in the whole value of alpha and 8 degrees of freedom. And so that confirms the 2.3060 critical value that we have. And I've just got the positive critical value stated here. Obviously, there is also a negative critical value, but it's just the negative of that value that you see. Alrighty, so let me come back and let's see where we are here. Computations. This is just the formula showing the mean computing d-bar, that mean of minus 1.556. Let's just see what we've got here and verify that we've got both of those shown correctly. So the mean of d-bar matches our minus 1.5556. Standard deviation of the differences. I didn't compute the 16.222. I certainly could compute that up in my table above. That's just the sum of the squared differences between each individual difference and their means. So you can verify that computation if you would like to. We can see that just by taking the standard deviation of the differences, we do get to the same result that we would get by using the formula here. So that works out for us. Then let's go ahead and compute the standard error of the differences. Standard error of the differences is the denominator of our test statistic term. And so we'll compute that by taking our standard deviation and dividing by the square root of sample size. Okay, so that standard error is 0.4747, and we can compute our test statistic. Test statistic we're going to compute by taking our sample mean, and I am going to put a parenthesis in front of that because I want to subtract my hypothesized mean difference. Close my parenthesis before I divide by the standard error. And so we get a test statistic of minus 3.2772. And got it in my formula. Also have it written over in my computation over here. All right, with a test statistic of 3.27, 3.28 if I round, we are definitely more extreme than the critical value, so we're going to reject this null hypothesis. Let's go ahead and compute the p-value and make sure that that verifies. Remember, the p-value is the probability of getting something this at least as extreme as this test statistic. And so I'm using my two-tailed t-dist function to find that probability, find that p-value. So I will give it the absolute value of my test statistic, and I'll tell it that we're working with a t-distribution with 8 degrees of freedom. And so I get a fairly small p-value, 0.0112 is the p-value that we get, and that is less than our chosen level of alpha, so that confirms our decision that we're going to reject the null hypothesis. All right, I'll go ahead and write my if function here, although we can certainly look at the result and we can come to the right conclusion, but let's go ahead and get the function to work for us too. So if my p-value is less than my chosen level of alpha, if that comparison comes out to be true, then I want my function to say we are going to reject the null hypothesis. Otherwise, we will fail to reject the null hypothesis. I like to write these functions based on p-values just because it's a little bit simpler that way. All right, so we're rejecting the null hypothesis. And then let's go ahead and do one more computation here to confirm that the confidence interval leads us to the same decision. And so we'll compute our confidence interval by taking the point estimate d-bar adding and subtracting a margin of error that we compute as the critical value of t times the standard error of the distribution. And so we've already computed the critical value of t. We've already computed the standard error of the distribution, so we can multiply those two together to get our margin of error. And then we will take d bar, subtract the margin of error to get the lower confidence limit, and we'll take d bar and add the margin of error to get the upper confidence limit. And so what we can say based on those computations is that with 95% confidence, the true mean difference in ratings between coffees is between minus 2.65 points and minus 0.46 points. That interval does not include our hypothesized mean difference of 0. Therefore, that takes us to the conclusion that we would reject the null hypothesis. Same conclusion, same decision that we made using the critical value approach and using the p-value. All right, so told you this one was fairly simple, right? This one is actually fairly close to the simple t-value test, that one sample t-value test that we had done, because essentially what we do when we do paired t-tests is we take those differences, and because we have a way to match them up, what we can do is collapse those to a single set of ratings, which is this mean difference, and that's what we're really testing. All right, that concludes this one, and we will pick up in another video.